Welcome to Hooke's Law Lab. Regardless of your major, when you're studying physics, one of the core things you will naturally learn is the causality principle. The notion that nothing happens without some cause behind it, even if such a cause is not apparent. However, you could also observe in the lab so far is that often the results of some experiments aren't as nice and clear like math models suggest. Instead of undermining the experiments, those deviations should be examined, and if it's a systematic error, the cause of these deviations can be found, like in projectile motion lab. If you remember when you plotted the experimental data and the math predicted model on the same graph, you could clearly see the pattern whereas the angle of the launcher was increasing, the distance traveled was drifting down from the values that are predicted by the projectile motion equations. Hopefully you had the curiosity and time to figure out that the reason for this decline in distance is the weight of the spring itself. Simply put, when we rotate the launcher angle closer to vertical, more and more of the weight of the spring has to also be pushed by the spring. Imagine we have a spring that is standing vertically, and you can see that the bottom half of the spring, in order to fully decompress, has to overcome not only the weight of the ball, but also the weight of the top half of the spring. In this lab we will evaluate Hooke's law, which seems very simple, yet when tested in the lab also has a bit of an unexpected result. We remind you that this video is not a substitution to the manual, and it's important that you read the manual in full, either before or after the video. Today we will try to experimentally find the spring constants of different springs and systems of springs. For that we will need some way to measure the force exerted on the spring and also the extension of the spring. So we will use our motion sensor for that. We could use scales to measure the mass and find the force from F equals to m times g, but it's much more convenient to use a force sensor directly. Once we are ready, we will add a piece of paper to the bottom of the spring, the position of which will be measured by the motion sensor. The mass of the paper is pretty small, so we can ignore it for the purpose of this experiment. We perform the experiment according to the manual, starting with a single red spring and measuring the initial position with zero force exerted on the spring. Next, we will add a load onto the spring and measure the force it exerted and the final position. The load must be heavy enough to clearly see the extension of the spring and be light enough so we are still in the elastic range of spring extension. If we overextend it, the spring will be permanently deformed and will not go back to its initial form. The elongation of the spring is the difference between final and initial position. We'll repeat it with different weights for getting a good dataset. Next, we'll do the same with the blue spring and the green one. Note that the loads for those springs are heavier, as their spring constants are bigger. Now we will set 2 springs in series connection and do the same with 5 different loads. Then we try 2 springs in parallel connection. The connector here is to keep the springs parallel to each other and can be ignored in calculations for this experiment purposes. And finally, we got a whole system of springs with both parallel and series connections. Now, before we even go into graphs and data analysis, please do a quick calculation of a few data points by hand. Calculate the spring constant for a single green spring from 2 to 3 data points that we have. Once you finish the data analysis, try to answer that question. Why the spring constants that you got from separate data points by hand did not match what you expected? Please answer this question in the discussion section. A small hint, the answer lies in different types of springs and how this type of spring is manufactured. A key term will be minimum load or initial tension. After answering this question, please rewrite the Hooke's law equation specifically for our experiment, including the new parameter. When you were doing the data analysis, you should have already seen that term and know its value from the trendline equation in Excel. What is its value for green spring?